Okay, everyone. All right, welcome back to the summer edition of the HEAD seminar. Today we're thrilled to have Ashwini Shenoy here, and she's going to speak about using the time evolution of an active regions for solar flare forecasting. And Ashwini is pursuing her MTech research degree at the National Institute of Technology in Karnataka in India. Her work lies in the interdisciplinary field of solar physics and machine learning and deep learning. Her current research focuses on leveraging deep learning algorithms to predict solar flares. And outside of her academic work, she enjoys learning languages, solving Sudoku puzzles, playing solitaire, and expressing her creativity through sketching and painting. All right, it's great to have you here, and please take it away.
Yes, so hi everyone, and thank you for the introduction, Olaf. So before I begin, I would like to give a shout out to my collaborators, my research supervisors, Professor Deepu Vijaysenan and Dr. Raghavendra B.S., my collaborators, Dr. Srijat Padimhattiri and Aditya HN from MCNS Manipal, Dr. Vinay Kashyap from CfA Harvard and Smithsonian. I also want to thank the Spark 3 project grant and Astro AI for sponsoring and hosting me this summer. Okay, so now to the actual topic. Oh.
We try to click on the, just click on the screen.
Oh, okay. Yeah, so we all know the sun, and as it turns out, sometimes the sun just spits out a large amount of radiation from here and there. And these radiations, we call them solar flares, and the here and there's, they're generally like regions of really high magnetic field called active regions. This radiation takes about 8 minutes to reach us here on Earth, and we can and we do measure this, and we do measure the amount of radiation that is ejected out of the sun in terms of the soft X-rays. And we classify the soft X-rays based on, we classify the flares into 5 different classes. You have the A, B, C, M, and X flares. Of these 5 classes, the M and X class flares, they are called the high intensity flares. They are of specific interest to us because they do affect our lives on Earth. Of course, not directly because the atmosphere protects us, but they do have certain effects, such as they can cause radio blackouts. Also, they can just, also anything in space is exposed to the high radiation, and it can actually damage the instruments in space. That's why we try to forecast these events before they occur, and this way at least we'll have some time to take up measures in order to safeguard our instruments, our people, or just be ready for the consequences of these flares. So what I do is I use supervised deep learning techniques where I have the input and I have the expected output. Using this, I try to predict a flare before it happens. Yeah. So my data, it comes from the Solar Dynamics Observatory. My data comes from the Solar Dynamics Observatory. It has this amazing instrument called the helioseismic magnetic imager. It records full disk magnetograms. That's just the spatial distribution of the photospheric magnetic field of the sun. So here, if you just take a look at the magnetogram, all the gray areas, that belongs to the background values of the magnetic field of the sun. But there are some regions over here which have these really dark regions and some really white regions. So these regions are what we call active regions. This is how active regions look. So the black and the white, they correspond to the 2 polarities of the magnetic field. And the HMI people, they were very kind, and they developed a high-level data pipeline which automatically tracks these active regions, and they have bundled it into a data product called the Sharp data product. So these four, they are part of the Sharp data product. You have the B phi, BR, B theta, and the line of sight components of the magnetogram. So that was about the input. But since we're doing supervised learning, we also need the expected labels. So we get the labels from the GOES satellite. So again, yeah, also I do binary classification. So I tell whether there'll be a flare or not. So my two classes are defined as follows. So I have the positive or the flare class, which contains samples where there will be a flare greater than or equal to M class in magnitude after 24 hours, and anything otherwise falls in the negative class. Now, once you have any model, you need to evaluate whether the model is performing well, and you have the performance metrics for that. These performance metrics, they are defined based on the kind or the type of data that you're using and the kind of task that you want to achieve or the problem itself. So in solar flare forecasting, there is this problem of high class imbalance. What this means is that we have way few examples for the positive class compared to the negative class. So as for example, so one of my data sets, there's only has only 4%, approximately 4% samples belong to the positive class. Everything else falls under the negative class. You can see the imbalance. So if we do not use the correct performance metric here, our model may learn to cheat its way, and that's a problem, of course. So that's why we look for performance metrics that are invariant to the class imbalance. This is where the true skill statistic comes into play. If you take a look here, this statistic or this measure is invariant to the class imbalance. So that's why we take TSS as our primary metric and F-score as our secondary metric. These are calculated from the confusion matrix, as you can see here. So what we did was we looked at the spatial distributions, or what we're calling field maps, of different properties of the active region. And using this, we tried to answer the question. So given the spatial distribution at time t, will there be a flare after 24 hours? So in order to do this, we have a base model which we train with the data, and that gives the flare no flare output. We wanted to use a deeper base model because it would be able to identify more complex features from the input. But in order to use deep models, we need more data, which we don't have. So to overcome this, we used something called transfer learning. And so in transfer learning, you have two data sets, dataset A and dataset B. So you train the model first on dataset A, which is done for a completely different task, but the inputs are similar to what you want to do. And then you retrain the model with your dataset. So it's an analogy would be, let's say it's easier for a physics major. It's easier for a physics major to get into astronomy or astrophysics than it is for a art history major, because they have to learn more things compared to the physics major, because they already have they already know enough things. So yeah, we do use transfer learning from the ImageNet database. So to repeat, our base model is a ResNet 18 model with image, which is pre-trained on the ImageNet dataset. We train the base model with different kinds of properties of active regions. So you have the line of sight magnetograms, the unsigned magnetic flux, the vector, the vertical current, the unsigned current helicity, the magnetic energy density, and the three components of the magnetic field. So the base model is trained with all these inputs, and you get all these different models. So if you look at the results for these models, you can see that the vertical current did the best, very closely followed by the vector magnetograms. After this, we looked into what our models had learned using an explainable AI technique called GradCam. So what a GradCam does is it produces a heat map based on how your model is viewing the input, or how your model processes the input. Based on that, it generates a heat map. The way you read the heat map is the brighter region corresponds to where the model found some flare signatures. So if you take a look here, the true positive case is where the model correctly predicted a flaring case. So here, the brightening is around the polarity inversion line, where the polarity changes. That's where the model found some flare precursors. Also, for the correctly identified negative samples, you see that there were no flare precursors that were identified by the model. So, of course, I do want to point out that for the false positives that the models generated, we could see something similar, and for the false negatives also, you could see something similar. But the takeaway from this is that we can be assured that the model is learning something. It is learning relevant things. What needs to be done is that we need to fine tune it further so that the false predictions are reduced. Now, if you look at the results over here, you see that most of the results actually, they are in the 0.7 range, right? They're all in 0.7s. So this got us thinking, so are they all looking at the exact same information, but only in a different form, or is there something new that they're all bringing in? So in order to look at this, we thought maybe we'll see if the common factor amongst all this, what if that's the complexity? So what we did was we calculated some complexity measures. So here you have the number of white pixels to the number of black pixels. You have the spatial complexity measure for the white pixels and for the black pixel, and the R value, which stands for, which is the sum of the, the R value, which is the sum of the flux around the polarity inversion line. So we just saw this, and as you can see from the plots, these features or these measures, they cannot be used to discriminate between the flaring and the non-flaring class, because there is significant overlap between the two. For the two classes. But what we do see is that there are patterns. There are specific areas of overlap. So what this tells us that we can curate our data set so that we just remove the other things and we just look at the area of overlap. We train our model with only the area of overlap so that it sees only the cases where it was getting confused, and hence it learns how to, separate them in a probably more complicated space. So that was with the point-in-time data. So earlier what we were doing is we were looking at just this sample here, and we were trying to predict if there'd be a flare here. Now, instead of that, what if we look at a video or the evolution of the active region for a time period of, say, 6 hours, and then find out if there'd be a flare 24 hours later. So to do this, we started out with the line of sight magnetograms, and we did a pilot study where we took each of these frames and we got the outputs of the ResNet 18 model, and we got the probability of flaring for all of those, and that we fed to an LSTM, a small LSTM network. So one thing is so the data is no longer just spatial, it's spatial temporal now. So you have features in both the spatial domain as well as the time domain. So that's why the pilot study has, the architecture involves two components. One is the ResNet 18, which primarily looks at the features from the spatial region, and the LSTM, which looks at the features from the time domain. So coming to the spatial domain, so generally when we look at image data and we want to extract any features from it, the way we do that is we design a certain filter. Let's say, take for example, edge detection. You design a filter for edge detection, and so you design a filter for edge detection, and then you just slide it across the image to get the edges from the image. Similarly, now instead of us designing the filters for the edge detection, what if we have something, or what if we have the model identify these filters on its own based on what it thinks is relevant, or what it identifies as a relevant feature? So that's where the convolutional layer comes into play. So the convolutional layers, they design these filters on, I mean, they learn the best features, the best filters for the features that are present in the inputs. And a convolutional and a connet or a layer, yeah, and a deep convolutional network, it just has many such convolutional layers. And as you go deeper into the model, it extracts more and more complex features. So here I've shown the output of some of the intermediate layers. So as you can see here, at least for the initial layers, you can still make out what the model is. I mean, you can still see and you can make out what features are being extracted. But as you go deeper, the the information starts getting more concentrated, and of course we cannot make sense of this, but the model can. Coming to the time evolution part, we use an LSTM. So the LSTM cells that we saw earlier, this is what they actually look like. An LSTM cell, it has this really amazing thing called the memory cell. So this thing over here. So the memory cell, it has the information, it has the actual information from the previous cells. Sorry, the previous frames. So if you remember here, you have multiple frames, right? But this frame is dependent on this previous frame in some way or the other. And that's what the temporal, that's the information in the temporal domain. So that information is carried in by the memory cell. In addition to the memory cell, the LSTM cell has 3 gates. The forget gate. The forget gate, it decides what part of the memory cell to retain. Sorry, what part of the memory cell to forget. The input gate, it tells what part of the new input to add to the memory cell. And the output gate, it decides what part of the memory cell should be included in the output for that particular timestamp. So we have, so our network has one LSTM layer with 10 such cells, and the output of all of those 10 cells, it goes into, so it goes into 3 dense layers, which finally give you the flare, no flare output. So these were the results that we obtained. So as you can see here, as compared to the point in time, the time series showed only a 1% increase in the performance. I mean, especially for the TSS. So of course, this raises the question, so should we go through all the trouble of looking at the time series when the results are so close by? So I still think yes, because there are some shortcomings of our pilot study. And I think if we find alternatives, or if we find ways to deal with those better, then maybe we can get better results. So one of the shortcomings is that, so here you see that there are different frames, right? So not all the frames are available for each samples. The data has a lot of gaps. There are so many frames that are missing. And the way we are dealing with it right now is the probability of flare that you get from here, for the missing frames, they're being set to 0. That may not be the best thing to do. Another thing is that we are taking the probability of flare value from here, right? So that's the output from this point. So instead of that, if we take this and feed this to the LSTM, that may yield better results. So so these are the 2 things that we want to explore in the future. And I hope that does give us better results. I mean, much better than the 1% increase that we see here. Also, another thing that I want to do is I want to repeat this for the other spatial distributions or the other properties. Also, I was intrigued by the complexity of the active region. So I want to see if there are models which I can use that are good with identifying, that can be better at identifying the model complexity. Finally, so for the point in time data, we did transfer learning from the ImageNet data set, right? So here also, I want to find methods of employing a similar transfer learning technique for the time series data as well. So to summarize, we looked at different active region properties, the point in time data, and using that, we tried to predict the flares. we found that the vertical current performed the best, very closely seconded by the vector magnetograms. We found that like what our model was learning was that whenever it predicted a flare, it was looking at the area near the polarity inversion line. So yeah, so that does instill some confidence that our model is learning something which aligns with the physical models of flare forecasting. Also, also the results of our results from the different features, they were very comparable and they were very close by. So that raises this question that are they looking at the same information but only in a different form? And is that feature or is that information in terms of the complexity? So this is, well, yeah. And also we looked at the time evolution of active regions to see if they'd be any better at predicting solar flares. We found that they're only slightly better, but if we do overcome some of the limitations of the pilot study, then maybe we can get better results there. Thank you.
Thanks, Ashwini. That was perfect timing. Do we have questions? Yes, please.
So first of all, it was a great talk, and I have a question about when you predict the solar flares, does the model kind of output like a specific time that it gets output? It's like
No.
Solar flares.
So it doesn't output the time. So the time or the prediction window is set. It's 24 hours. So it predicts whether there'll be a flare after 24 hours. It's a yes or no answer. Yeah.
Thank you.
I think you were first.
Sure. So for the time-dependent training,
Yeah.
Are you training are you still training the spatial part of the model as well, or are you just training the LSTM?
Yeah, so they're trained separately. So they're not trained end to end.
Have you considered training them together, or what that would look like?
I have not tried that, but yeah, I mean, I was planning to do that for like in the future step, and I said that I'll use the embeddings. So I said that I'd use this one, right? So for this one, so I was planning to train them end to end when I work with this.
Very nice, thank you.
Rafa?
Thank you, Ashwini. Can you elaborate on what is it exactly that you think are shortcomings of your current model that could still lead to improvement when you use the time series? I didn't quite catch. It looks like your results suggest that one image at a particular time is enough to predict whether there will be a flare in the next 24 hours. I would have expected, as you did, that when you have the time series, the evolution of that image would be more accurate. But I didn't quite follow what is that you plan to do to make this result better when you use the LSTM.
Also for the time series. Okay. So so if you see here, the results, they are still in the point. I mean, this is not good. The maximum value TSS can take is 1, and we're still in the 0.7s. So I started looking at the time evolution because so the motivation for that was that that's how okay. So the way the complexity or the way the active region evolves, that's how so for example, let's say so one thing that so if there's more mixing of the two polarities, if the two polarities are coming closer together, that increases the chances of a flare. But if they're going farther apart, then there won't be a flare after 24 hours. So if we just look at the point in time data, you don't know whether they'll be going closer in the next 24 hours or whether they'll be going far apart. But if we see some data which shows that they will go closer or they will go farther apart, if we have such flare, if we have that information, then maybe that would help us predict things better. That was the motivation, actually.
It's not doing better.
It's not doing better, yes.
The question is why do you think that is?
So yeah, so the reason for that is that I have a lot of gaps in the time series that I'm giving in, and all of those gaps over here. So so for the frames, the frames that are missing, the probability of flare that I feed to the LSTM, that is I'm just taking that as 0. which is not the, which may not be the ideal, which may not be the ideal thing to do. So I was looking at ways of maybe like better feeding in on like ways of dealing with the gaps in a much better way. Also, another thing was that maybe probability of flare may not be the best thing. There could be some other information which I could give into, such as the embeddings. They are much better. I mean, these are much better than the probability of flare itself in terms of information content. So maybe give that. Yes.
Yes.
I was wondering, in that results plot that you were talking about, what is the y-axis? And can you maybe explain what it's exactly? Is that?
Oh, so the y-axis. So okay. So you have two things here. You have the F-score and the TSS. So the TSS varies from -1 to 1. F-score varies from 0 to 1. So that's why it's this 0 to 1. That's just the value that F-score or TSS take.
What does that represent? Like, is that like the?
So these are performance metrics. Yeah, so they quantify how well your model is doing.
I'll go back.
Yeah.
That's
So yeah, here. So they were defined. Yes.
I have a question on the data. So you said that for training the model, you used transfer learning specifically from ImageNet. Can you
Right.
explain a little bit more about how the data from ImageNet looks like? And how
So the ImageNet actually has 1,000 classes and it is trained on a lot of images, like 1,000. So you have cats, dogs, and everything. So you have 1,000 classes, and there's a lot of data that the ImageNet dataset contains. So any model that is trained on the ImageNet dataset should be able to extract features really well from images. Right. So we do transfer learning here because at least the initial or the basic information that so here at least the basic stuff that needs to be extracted from the image, that can be the same for both ImageNet and the Solar data, because they both are like images. So that's why at least that part I needn't train. I can only focus on the more deeper complex things. I mean, I can use my data to train only the more complex, to train the layers that extract more complex features.
I have a question on that.
Mhm.
So, and the models that you use, when you have your output models and it produces like these extractions, feature extractions, do you somehow like use those extractions to further train the model, like use the output from your model to retrain it again? Is there any room for that? Or?
No, sorry, could you just elaborate on that?
Oh, I was just thinking well, I'm not new to, I'm new to like this space, like I don't really know exactly what's going on at all. But I was just thinking like, using the, so you have like your output from this model, which is like the feature extraction. When you're training your data, or you're training your model, is it possible to like use that extraction that you got from the image that you get,
You mean this?
yeah, I guess like using the features extractions to retrain the model that you already have.
So okay, so just first get this and then feed this
Yeah,
to feed this back.
I don't know if that makes sense.
No.
I don't know if that question.
Well, I mean, you can use this to train something else, but of course this cannot go back to this because obviously they have different dimensions. So these are 7 by 7 images. These are 224 cross 224 images. Yeah.
Okay. I suggest that you can continue asking Ashwini either by email or now after the talk or while eating ice cream. But I suggest we get her eat her well-deserved pizza slice. And thank you so much for coming. We'll have our next head seminar in 2 weeks' time, and see you then.